to do a problem that asks me to predict K at one temperature given K at another temperature. And the equation that I need to use for this, the equation that gives me the relationship between K and temperature, is the Van't Hoff equation, which looks like this. So it's the natural log of K2 over K1 equals delta H for the reaction as written over R times 1 over T1 minus 1 over T2. Okay, so you can see your T1 and T2 in there and your K1 and K2 in there, and it doesn't matter which one you choose to be 0.1 and which one you choose to be 0.2 as long as they're paired correctly. So as long as my 78.3 goes with my 523. And so what I'm going to be looking for here is K2. I'm just going to pick that because it's my new K. And I'm given K1 and I'm given T1 and T2. But I also need delta H. So let's figure out what I can do about that. I have tables of thermodynamic values that I can use to calculate delta H for this reaction, and I can use the delta H's of formation that are in that table and use Hess's law, which says if we add up the delta H's of formation of the products, because we're effectively making them using the standard state elements, and subtract the delta H's of formation of the reactants because we're breaking them down in this theoretical process, then we should get delta H for the reaction. So if I look up those values, what I find is that delta H equals negative 287.0 kilojoules per mole, that's the delta H of formation of PCl3, plus 0, which is for chlorine, because chlorine is as Cl2 in its gas state is a standard state element. And then I'm going to subtract the delta H of formation for PCl5, which is minus 374.9 kilojoules per mole. I'm running out of space here. Okay, so that is my, that's good. That should give me delta H for this reaction, and that comes out to be plus 87.9 kilojoules per mole. Okay, so now with that value, before I even go into my calculation, I can make a prediction. This is an endothermic reaction because it has a positive delta H. And so that means that heat can be treated as a reactant in this equation because heat is going in. So now that I know that, I can actually predict whether K is going to be bigger or smaller. So I'm increasing the temperature. I'm going from 523 here to 800. So that's an increase in temperature. So I'm adding heat. I'm adding extra heat. And so whenever you add anything to an equilibrium, it shifts away from that addition in order to compensate. And that's Le Chatelier's principle, in order to reestablish the equilibrium. And so since heat is a reactant, when I'm increasing temperature, I'm adding heat, it should shift away from that, so it should shift to the right. It should make more products. And so since products are in the numerator of any K, so this is K here, PCl3, Cl2 over PCl5, these things are going to get bigger, larger, when I add heat, because I'm shifting the equilibrium to the right, and I'm increasing the concentration of the products, and this should get smaller. So this is a fraction, so if my numerator becomes larger and my denominator becomes smaller, that means K overall should get larger. So that's my prediction. Let's see if it works out to be that way. So the first thing that I need to do is isolate K2 in this whole equation. And that can involve some kind of ugly algebra. What I'm going to do first is I'm going to simplify this natural log expression. Anytime you take a natural log of a fraction, it's the same thing as taking the natural log of the numerator and subtracting the natural log of the denominator. So I'm going to do that first. And then that whole thing equals what I have on the right, same thing I had on the right before, Okay, so that's my revised form of the equation. And so now I'm going to isolate K2 by adding the natural log of K1 to each side. So natural log of K2 equals natural log of K1 plus delta H over R 1 over T1 minus 1 over T2. Now I could go further and I could simplify this by taking all of the stuff on the right as an exponent of E, and that would just leave K2 on the left. But I'm going to, and so I can write that, I can do that algebraic step, but I find it easier to just substitute numbers at this point and deal with the exponent later. So I'm going to substitute numbers. Okay, so this is natural log of 78.3 plus our calculated value of delta H was 87.9, and this needs to be in joules because R has joules in the units. So I'm going to add my times 10 to the third to make it into joules from kilojoules. Okay, over R, which is 8.31 joules per Kelvin moles. And now I can multiply this by the reciprocals of my two temperatures. So my T1 is 523 and my T2 is 800 K. If you don't have these in K, they need to be in K when you plug them into this equation. Okay, so if I plug all of this into my calculator, I end up getting 11.36. Okay, but that's not the answer because I still have to take out that natural log. So this is what the natural log of K2 is equal to. And so in order to isolate K2, I'm going to take E to the 11.36. So if I do that, I get let's do that again to make sure. Okay, so I get a rather large value. I get 8, I'm going to write it in scientific notation, 8.58 times 10 to the 4th. Okay, and these K's are unitless, so I am done. But let's go back and revisit our initial prediction. We predicted that the equilibrium would shift to the right and that K would get larger. And indeed, at this higher temperature, K is quite a bit larger than it was before. It goes from 78.3 to 8.58 times 10 to the 4th.